In this pre-class question, we're asked to find where is the net magnetic field 0. On the top here, we have a long wire. It's carrying current, carrying current 250 milliamps into the page. That's what the X means. And the lower wire carries current 125 milliamps out of the page. So we'd like to find where the magnetic field is going to be 0. So first we have to decide on the spot. Is it above this wire? Is it between these wires? Or is it below this wire? Let's see how we're going to figure that out. So we'll redraw our two wires, one here and one here. Let's label them wire 1 and wire 2. Current 1, current 2. Oops, current 1, current 2. So our magnetic field due to this wire makes big circles around the wire. Let's look it up here on the top. The direction of my magnetic field up here on the top due to this wire, the orientation of the circles goes with my fingers. So it's a big circle around the wire. My thumb goes into the page. The orientation of the circles is around this way. The magnetic field at the top is a tangent. There's my magnetic field B1. I1 has a large current, 250 milliamps or 0.25 amps. Okay, let's find the magnetic field at this point due to this wire. So up here at this point, the magnetic field makes big circles around the wire I2, something like this. The direction of these circles is you put your thumb with the current and your fingers show the orientation of the circles, coming around this way. The magnetic field at this point is a tangent to the circle, so it's going to be horizontal and it's going to point to the left. I2 is a small current, 0.125 amps. We're far away from a small current. We're going to get a small magnetic field. There's B2 up here. So this can't be the spot where we get a net field of 0. Okay, let's try in between the two wires. I'm going to do a new diagram. I1, I2. In between the two wires, let's say right here, the magnetic field due to current I1 makes big circles. The orientation is the same. Your thumb goes into the page. Your circles come around this way. The direction at the bottom of the circle is a tangent. So you put your thumb with your wire, you line up your knuckles with the bottom of the circle, and you see that your fingers point towards the left. There's our B1. Okay, what about this wire? Well, we know we've got big circles around the wire. Put our thumb with the current, and we use our fingers to show the direction of the fields. And the direction of our magnetic field right here, due to this wire, will point to the left. There's our B2. Okay, this can't be right. Both fields point to the left. They can't sum up to be 0. So our answer is the magnetic field must be 0 down here somewhere. Okay, let's get to work on that one. I've cheated a little bit and I've pre-drawn my circles on the page. So we've got wire 1 and wire 2. Wire 1, let's use blue for that one. Wire 1 has current of 0.250 amps. Wire 2 has current I2 equals 0.125 amps. We know that the magnetic field is going to be 0 down here somewhere. So let's get the direction of the two fields and the relative size. The magnetic field due to wire 1 makes big circles. Your thumb goes into the page. Your fingers show that the orientation of the circles are around this way. That's been the same in every one we've tried. The direction of the field at this point is horizontal, and it has to be in the direction that the field is pointing. That's to the left. So our magnetic field B1 points to the left. If we think about the relative size, here we're far away from a big current, so we have about a medium field. Okay, let's deal with I2 next. The wire carries current going out of the page. Make a circle with your fingers to show the orientation of the circle is coming around counterclockwise. The direction of the field at this point is going to be horizontal. That means it's going to point to the right because our field is coming around to the right at the bottom. Here, we're close to a small current, so we're going to get about a medium field. So, for where our net magnetic field is going to be 0, we know the fields have to be equal and opposite. we've taken care of the opposite part by identifying our point down here. Here they can't be opposite, here they can't be equal, here they can be equal and opposite. So we've got opposite dealt with. Now let's deal with equal. Magnitude of B1 equals the magnitude of B2. The magnitude of B1 is mu naught times I1 over 2 pi times R1. Let's show R1 in our diagram. That's the distance between wire 1 and our point. And the magnitude of the magnetic field created by wire 2 is mu naught times I2 over 2 times pi times R2. Let's show R2 in our diagram. It's from our wire to our point R2. So now we'd like to solve it to find our distance. What we might notice here is that R2 plus 10 centimeters equals R1. So there's a relationship we can use. R2 equals R1 plus 10 centimeters. We might also notice that I1 is 0.250 amps. I2 equals 0.125 amps. If you're a numbers kind of person, you can leave those numbers in and go ahead and use them. If you're a symbols kind of person, you might notice that I1 is equal to twice I2. I'm a symbols kind of person, so I'm going to use this relationship. Okay, so mu naught times I1, which is 2I2, over 2 times pi times, oh my goodness, I messed up here. I said R2 was R1 plus 10 centimeters. That's not true. R1 is R2 plus 10 centimeters. Let's just get that fixed up. There we go. Now we're all set. Okay, mu naught times 2I2 over 2 pi times R1, which is R2 plus 10 centimeters, equals mu naught times I2 over 2 pi R2. Okay, let's see what cancels here in this equation. Divide both sides by mu naught, divide both sides by I2, multiply both sides by 2 pi. Now this is looking nice and more simplified. Cross multiply our R2 up here, 2R2. Cross multiply R plus 10 up here. Let's get our R2s on the other side. So 2R2 minus R2 is R2 equals 10 centimeters. So the net magnetic field, B net, equals B1 plus B2 equals 0 at 10 centimeters below wire 2, or below the lower wire.